Hey everybody, here's our Unit 3 review. Don't forget our test is this Friday. Alright, first and foremost, go ahead and write your name at the top because some of you do all this work and you do not get credit for it. Don't forget, sometimes these papers get mixed up. Put your last initial at least, right? Write your full name. Okay, anyway. So our first three questions here are about light equations. The first one says, if the wavelength if the wavelength of an energy wave increases from 5.22 to 8.99 meters, what will happen to the frequency? So it's asking us about frequency here. So let's look at our popsicle stick. You can have a popsicle stick when you take this test. There's our trusty popsicle stick. Don't forget that this right here means wavelength. That is lambda. And so anytime we're talking about meters or nanometers, we're talking about lambda. And then over here, we've got obviously frequency and energy. Those ones are a little bit easier to remember. So let's check. It says if the wavelength increases. So what happens when wavelength increases? Over here, I can see that my frequency decreases. So that's what I would put as my answer. Frequency decreases. Cool. I think with that, you can figure this one out on your own. Man, maybe I should have mentioned at the very beginning, but the last time I made a video like this, I skipped every other problem, and you were supposed to do them on your own and turn in the whole paper, and some of you only did the ones that I did. So you do this one. All right, here, I'm not going to do the whole thing for you, but I am going to tell you how to figure it out. So it says Saturn's rings emit yellow, green, and red colors. Remember that colors are part of the light spectrum and they can be measured in wavelength and frequency. It says list the colors from lowest frequency to highest frequency and explain why the colors are arranged this way with respect to wavelength. So here, I know we haven't gone over this, what this means. This is called scientific notation. But for the most part, we can just ignore that. We can ignore that, and that, and that. And we can just look at these numbers here, 5.7, 4.95, and 6.2. And we'll use those numbers just like regular numbers, right? So we can see that this one is the smallest number, and then this one, and then over here, red is the largest number. So let's think about what they're asking us and what they've given us. They've given us wavelength, and they're asking us to put them in order of frequency, right? So we just said over here a minute ago that wavelength and frequency have an inverse relationship. When wavelength goes up, frequency goes down, and when wavelength goes down, frequency goes up. So using that information, using your popsicle stick that you're allowed to have on your test, put these in order from lowest to highest frequency. All right? All right, let's move on to the next part. Now, this part is straight from your notes. There's nothing to figure out. I will say, oops, we made a little tiny mistake. We should have given you a little bit more room. But really what we got to remember is two things. Number one is these energy levels. These energy levels refer to two things. First off, when we're drawing an atom, the energy levels refer to the rings. Whoops, I'm sorry, this is just ugly. Maybe I can do a better job. Let me try it again. Okay, let me try a freehand over here. That looks like a smiley face. All right, so the energy levels refer to the rings that we draw. For instance, energy level 1 would be the first ring, energy level 2 will be the second ring, and so on and so forth. But also, these refer to, we cannot forget, our periodic table, right? Energy level 1 is the first period, and energy level 2 is the second period, and so on and so forth. So don't forget that, okay? But again, this chart is straight from your notes. The sub-levels that we have are in the first energy level. Remember, the first energy level can hold an S sub-level because it's only one energy level. The second energy level can hold an S and a P sub-level. The third energy level can hold an S, a P, and a D sub-level. Let's put commas to separate them. And then the fourth energy level can hold an S, a P, a D, and an F. And then the number of orbitals. So these are the streets. These are the houses, if you guys want to remember that. These are the streets. These are the houses. Then these must be the rooms. And the total number of electrons are, electrons. So an S house, remember, has one room. A P house, so an S house has one room. A P house has 3 rooms. Remember this pattern? An S house has 1, a P house has 3, a D house has 5 rooms. And you can probably guess what the last one is. 7 rooms. So total number of orbitals, 1, 4, 9, and what's that? 12, 13, 14, 15, 16 total orbitals. And total number of electrons. Well, how many electrons can fit in each room? It's 2. So 2 electrons in one room, 2. Don't forget that the total number of electrons is also equal to this equation here. 2 times, I'll write it up here, sorry. 2 times n squared. So in the first energy level, n equals 1. 2 times 1 squared is equal to 2. In the second energy level, 2 times n equals 2 squared. 2 squared is 4 times 2 is 8. 8 total electrons. In the third energy level, now don't forget, this is 3 squared, not 3 times 2. So 3 squared is 9. 9 times 2 is 18. 18 total electrons. And then the last one, 2 times 4 squared is equal to, where am I getting these numbers from? 1, 2, 3, 4. It's the energy levels. 1, 2, 3, 4. Right? That's what n is the energy level. All right, 4 times 4 is 16. 2 times 16 is 32 total electrons. All right, cool. All right, now here's the bulk of what we did, right? Orbital notation and electron configuration. Let's look at potassium, bromine, iron, copper, and beryllium. I'm not going to do all of them for us. Let's start with, well, we've done potassium so many times. Let's start with bromine. So the first thing we got to do is find bromine in our periodic table. And if you forgot, bromine is over here. It is a halogen, and bromine is number 35. So that means bromine has 35 electrons. And we have to fill in these electrons, remember, with the rules that electrons are cheap, electrons don't like to share rooms if they don't have to, and one will always take the top bunk and one will always take the bottom bunk. So let's fill in 35. We'll go fast on this one. 1, 2, top bunk, bottom bunk, 3, 4. Don't forget to do it like this. We'll go up, 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 bottom, bottom, bottom bunk. That's 10, 11, 12. Every time we're in one house, we separate them out. 13, 14, 15, 16, 17, 18, 19, 20. We come to a bigger house. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. That is it. Let's write out this electron configuration. In the first energy level, in the S house, we've got 2 electrons. Second energy level, S house, we've got 2 electrons. Second energy, P house, we got 6 electrons. I'm just translating all of this. 3s, 2. 3p, 6 of them there. 4s, 2. 3d, 10. And then finally over here, 4p, 5, not 6. 1, 2, 3, 4, 5. All right, cool. Let's check out copper together. Let's find copper in our periodic table. Copper is right here. Copper is number 29. Not quite as many electrons, but still quite a bit. All right, copper has 29 electrons. So let's do this one. All right, we got 1, 2, 3, 4. Don't forget to do it like this. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, this is where we slow down a little bit. Remember what I said, when we get to the end, we chill out and we make sure we got it right. One big house, 5 rooms. We have to fill them like this. They each take a separate room. That's 23, 24, 25. Then they don't want to spend money, so they'll come back around. They'll share rooms. 26, 27, 28, 29. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Right here we got 3g9, and we're done. Okay, don't forget, you need to do potassium on your own. We've done this one a bunch. Then this one has 19 electrons. You need to do iron on your own. This one has 26 electrons. And you need to do beryllium on your own. Beryllium has only 4 electrons. That one's super easy for you. All right, finally we get down here to electron configuration. Now, some people were getting confused about what, long electron and noble gas meant. Long electron is just a regular electron configuration that we did. And you really need to know these other things as well. What energy level is the valence electrons on, which is the answer to that is always going to be what's the highest energy level. And then the number of valence electrons. We practice this quite a few times. So I'll do a few of them with you here. And then you can do the rest on your own. Let's see, which ones do we want to do? I'll help you out. I feel like these two are pretty easy, so you can do those. I'll help you out with vanadium first. Let's find, I forget where that one is on our periodic table. All right, let's search it up. Man, I'm always tempted to look right here. Oh, geez. Is it right in front of me? Did I miss it already? There it is, vanadium. We got it. So vanadium is number 23. We can see here it's going to be in the 3D. Actually, I kind of gotta like have this periodic table up here while we do this. So let me open that up real quick. All right, here we go. Okay, so here is vanadium. I need to start at the beginning and write everything down. Now, some of you are really good at this, but if you've forgotten, what we have to do is we have to start here. And what I said was we're kind of taking a census. If this is the vanadium neighborhood, then we have to count everybody in every street, in every house. So what we're saying is in the first street, in the S house, 2 people live there. Hydrogen and helium live there. In the second street, in the S house, 2 people live there. Now, some people would be tempted to go straight down to the third street, but we have not finished the second street. We got to come this way. We got to finish that street because there's a P house. So also in the second street, in the P house, 1, 2, 3, 4, 5, 6 people live there. 2P6. All right. In the third street, we're getting there quickly. In the S house, 2 people live there because every house is full. All right. Also in the third street, again, don't skip. We're still here in the third street. Third energy level in the P house, 6 people live there. Excellent job. All right, now we're at 4S. 2 people live there. Now don't forget, once we get here, if we get into the d orbitals are always 1 energy lower, 1 energy level lower. So this is going to be 3D. And you don't have to memorize that. You're going to get this periodic table, this exact periodic table when you take the test, all right? And then here, like we said, at the end, we need to slow down and count each one. So it's 3D, 1, 2, 3. Vanadium ends on 3D, 3. Excuse me. Now over here, it tells me to do the noble gas configuration. I kind of wrote a little bit too far this way, but I have enough room, so I'll still do it. So don't forget how noble gas configuration works. Noble gas configuration is like this. It's saying, look, I'm still going to go from here all the way to here. I'm just going to skip a little bit. After a while, you realize it just repeats over and over again, and everything is full. Every house is full. Every street is full. So I'm just going to say, look, I know first street is full. I know second street is full. And I know the third street is full. So the end of the third street is argon, right? The fourth street is not full. I have to count them again. But first, second, and third street are full. So instead of counting them, I'm going to start at argon. And I'm going to put that here in my bracket for the noble gas configuration. I just want to be very clear. This is 2 different answers. This is my long form configuration over here, and this is my noble gas configuration over here. Okay, so again, I'm just going to do the configuration just like normal. I'm just starting here. What comes next is going to be 4s2, just like we just did. 4s2. And then again, we're going to end the same way, 3d3. Okay, so what I really want us to notice is that no matter what, your long form configuration and your noble gas configuration will end the same way, 4s2, 3d3, 4s2, 3d3. It has to. If it doesn't, you made a mistake, all right? What we've done is just we've replaced all this with AR. Now, those of you that listened and caught on, I probably sound very repetitive, but that's okay. All right, so the energy level of the valence electrons. So how do we find that? Well, first we look at these large numbers here. The large numbers tell us the energy levels. What is the biggest large number that I have? Now, it's not always the last number. In this case, it's 4. So the energy level that the valence electrons are on are energy level 4. I'm just trying to find the highest one. So once we write that down, now I got to go and find, well, how many valence electrons are there? And I know we said transition metals are kind of weird, but for this unit, we're just going to use the highest energy level available to us, which is 4. And we're going to count every electron. Whoops. We're just going to count every electron that's in there. So that's just going to be 2. So that's going to be our number of valence electrons is just 2. And it's the same here as it is in the noble gas. It should be, right? All right. Good job on that. Let's check out another one. Let's see, aluminum or selenium? Selenium's the biggest one. I'll let you do selenium. Let's check out aluminum together, and that'll be the end of this. Don't forget, you are responsible for doing every question here. Man, I lost my periodic table. There it is. That's my beautiful wife. I like to have her as my background. Okay, let me get everything back again. Okay. All right, let's do aluminum. Okay, let's find aluminum. Here we are. Again, we need to go from the beginning to the end, and we're going to take a census. We're going to count every single person that lives here. We're going to start always starting at 1s. How many people live in the first energy level? 2 people. Hydrogen and helium live there. Cool. Okay, now we're on street number 2. 2s2. Cool. Don't skip. Go straight across. Now we're in the P house. 2p, and there are 6 of them. 6 people live here. 1, 2, 3, 4, 5, 6. Now we're in the 3s. Now we're getting close, but we're not quite there. The S house here is full, so we can just write 3s2 because we know it's full. And now we slow down. There's no d orbitals here, but we got that third p house. And the third p house is not full. Only one person lives there, and that person is aluminum. So 3p1. Okay. How do we do the noble gas? Well, we can skip the first street and we can skip the second street by going to the noble gas that comes before aluminum, neon. We're going to use neon as our noble gas. It's always the noble gas that comes before it. Don't forget, it has to be one of these guys. It has to be. It's almost always neon or argon, but every once in a while it'll be krypton. All right, so we're going to use neon in our noble gas configuration. And what we're saying is we're skipping all of this until we get to neon, and then we're starting here. So what comes after neon? 3s2. And then again, we're going here to 3p. Only one person lives there. 3p1. Notice again, we're ending the same way. 3s2, 3p1, 3s2, 3p1. Okay, what is the energy level of the valence electrons? Well, I've got energy level 1, energy level 2, and energy level 3. I got to go with the highest one. It's going to be energy level 3. Now on this one, don't forget, we have to count every energy level, and we have to count every electron that is in those energy levels. So in energy level 3, I've got 2 electrons here, and I've got 1 electron here. We're going to add those together, and we're going to get 3 valence electrons. That should make sense because 1, 2, 3 aluminum's in column 3. Okay? All right, I wanted to throw in this one extra here, 6p5. I wrote this whole thing out. This is the electron configuration for astatine, AT number 85, one of the rarest elements on our planet. It's this one right here, right? Now, what I want us to see is about the valence electrons. Let me move this out of the way so it's a little more clear. So it doesn't matter. Look, I've written out the whole configuration. This is really confusing, I know. But if you follow it slowly, you'll see it gets you all the way down to number 85. You'll notice here I've got some f orbitals and d orbitals, and it's all mixed in, it's all mixed up, right? But no matter what, if I'm trying to find valence electrons, I'm still always looking for the highest energy level. I'm just looking at the large numbers first. I can tell that some of us get a little bit overwhelmed when something kind of crazy comes at us, but I promise you, everything we learned is still the same. And so, if you look here, what is the largest big number that we have, right? So here we got 5, 6, 4, 5, 6. I think we can all see that 6 is the largest number that we got there, right? So let's underline both of those 6's. Cool. And let's just think about what it's asking us. How many valence electrons? Well, how many electrons are here? Right here, I've got 5. And right here, I've got 2. It doesn't matter that we didn't even talk about how f orbitals work. It doesn't matter because that's in the 4th energy level, and I don't care about that. All I got to do is take those 2, add them to those 5, and this is going to be 7 valence electrons, right? If we look over, that's for this element here, astatine. And astatine is in group 7A, and we know that group 7A has 7 valence electrons, so we're correct, right? 7 valence electrons, good for us. Now, you don't have to write this down. I just wanted to give you a heads up. There may be a problem like this on the exam, and I don't know. I don't want it to be the very first time you saw it, but we do the same thing. We're going to do the same thing. We're just going to use the highest energy level and the electrons that are there, okay? If you have any questions, let me know. Don't forget, if you do this whole assignment and turn it in completed, you get 5 extra points on your test. I know that doesn't sound like a lot, but man, that really bumps up a lot of people's grades. Please take the time to do it. It's not very difficult, and I did half of it for you. So